So in our last lecture video, I kind of briefly introduced what a pericyclic reaction is. And a pericyclic reaction is basically a reaction without any ionic intermediates or free radicals. So most of our reactions that we've seen before are polar mechanisms, where we have a very clear nucleophile and a very clear electrophile. There are several different kinds of pericyclic reactions. The ones we're going to focus on in this chapter are primarily the cycloadditions, specifically the Diels-Alder reaction. And so one of the questions to ask is, how is this an addition reaction? Well, we're adding a molecule across double bonds, so that's why it's an addition reaction. And so it falls still under the category of electrophilic addition reactions that you learned in Organic 1, but it's a very special kind of electrophilic addition. Now, there are other kinds of pericyclic reactions in which we rotate electrons within a molecule on its own, where we move around the pi bonds. I do want you to be aware of them and what they are, but we're not going to focus too much on them. There's a lot in your reading about, conrotary and disrotary. Just have a gist of it, but we're not going to be tested on it, just to get a sense of what those are. We will talk about some aspects of it a little bit. Electrophilic reactions are basically you're going to end up rotating your double bonds, then you end up closing a ring. Sigmatropic, which we actually see in vitamin D. That's actually how vitamin D works. With light, it rotates your pi bonds in the molecule around. But you're rotating your double bonds, and you end up moving them around that you open one side of your molecule but close another side of your molecule. So take a look at some examples of those in your book. So we're going to focus more on pericyclic reactions as it pertains to the Diels-Alder reaction. And like I said, there are others, but that's our focus. Pericyclic reactions have a couple of general rules. The mechanism is concerted, so everything happens at one time. We don't actually have any intermediates, but we do have a transition state. We are moving the electrons around in a closed loop. So all of the pericyclic reactions do that. What ends up happening then, because we're doing that, is the transition state is a cyclic molecule. And for the Diels-Alder reaction, the pericyclic, the transition state resembles an aromatic molecule. It's not, but it resembles it. And because these are nonpolar reactions, the polarity of the solvent generally do not have much of an effect on the reaction. Now, there are some modern studies about things in the lab where you might have some effect, but it's not the mechanism that it has an effect on, like we saw with SN1, SN2. It might have more to do with how it dissolves the materials and how it might affect the rate of the reaction as it pertains to other parts of your molecule being able to interact and how close they interact and things like that. But in terms of the mechanism, it doesn't have an effect on the mechanism. And this is significant because we can use wider ranges of solvent to do these reactions that can dissolve your material. And so that is kind of important. Now, we oftentimes see Diels-Alder reactions done in nonpolar solvents, but they can be done in other solvents. So when I do them, I've done them in many different kinds of solvents. So here's an application of the sigmatropic that I mentioned before. Vitamin D, essentially how it works is that you have a pericyclic reaction, actually two of them. So we have a sigmatropic reaction happening, and we have an electrophilic reaction happening. And we see that we actually open up the ring in light, and then we do some rearrangement. So we do a sigmatropic rearrangement, and that's what vitamin D, what's happening when we biosynthesize vitamin D in the body, is that these reactions are actually happening as a consequence of light. And that's why, other than getting vitamin D through food or vitamins and things like that, this is what's going to happen in your body. It's going to take these molecules and it's going to rearrange them to make your vitamin D. And that's why you need sunlight, not that you go out and get like gobs of sunlight. You just need a couple minutes of sunlight every day to synthesize your vitamin D. Now, if you have darker pigmented skin, this is harder for you to do because less light goes through your skin. It gets absorbed into the layers of your pigmented part of your skin, because darker skin is only pigmented on the very outer layers. It's the same color in the lower layers of your skin, but it still happens. Okay. Now, the Diels-Alder reaction, like I mentioned before, is the pericyclic reaction. We call it a 4 pi plus 2 pi electrons because one of your molecules has 4 pi p orbitals, or 4p orbitals that are associated with the reaction. So your 4p orbitals, and the second one has 2 p orbitals associated with the reaction, and it's an overlap of these orbitals that causes the reaction to happen. Now, in the Diels-Alder reaction, essentially we're going to take one molecule called the diene, which is very obvious why it's called a diene, and the thing that likes it is called a dienophile. And we can very easily and very quickly build libraries of these cyclohexane rings with all sorts of things that whatever we want on the molecule, you just envision it on what you start with, and that's what you can end up with. So if I start with A, B, C, D here, and I have X and Y on my structure, I can build that in. So I can build in, I'm sorry if you can hear my dog snoring, but you can build in all sorts of complexity into your reactions. Because it's concerted also, a lot of things about the stereochemistry and regiochemistry become quite conserved, and we'll talk about that more. So let's go over the mechanism. It's fairly straightforward. And again, remember, it's not going to be very apparent to us what is our electrophile and what's our nucleophile. We'll actually discover that more when we're in class. But it's a cyclical mechanism, and so we draw kind of in a cycle, and I'll kind of explain where your arrows are going, but where they're starting, which part they're starting, it's a cycle. So it's a big circle. You know, rings don't really have a beginning or an end, right? So essentially this double bond, this pi bond, is breaking on your diene, and we're forming a sigma bond between the diene and dienophile. The pi bond here breaks and throws its electrons between, in the sigma bond between the 2 pi bonds, so we form a pi. And here we're going to break a pi bond and use that pi bond to form a sigma bond. So what does our transition state look like? Let's draw that. It's going to very much look like, okay, so we're going to have some sigma bonds being formed here. We're going to have a pi bond being formed here. We're going to have a pi bond being broken here, a pi bond being broken here, and a pi bond being broken here. So if we kind of, it's not exact, but if we kind of look at this transition state, right, it kind of looks like the delocalization in benzene. And that's one of the reasons, it's not quite, but one of the reasons that this is relatively stable. But you always form a cyclohexene ring. And the double bond that forms is always going to be on the diene side. So if you were to have a problem where you had to figure out what did I need to start with, is look for where the double bond is. And this side of your molecule would have had to be the diene of your molecule. So wherever the double bond, the last double bond ends up. So, like I mentioned before, we have 4 pi electrons, or 4p orbitals, interacting with 2 pi electrons, or 2p orbitals. That's why we call it 4 plus 2. We get the molecule forming, and the conversion of p orbitals to sigma bonds is generally a negative delta H. And so we can see that we can use that information to figure out what's going on in the molecule. Now, one of the things to think about is, since this molecule is going from 2 to 1, this is not entropically favored. So delta S is actually negative. So this is not an entropically favored reaction. So it's not an entropically favored reaction, because in terms of dispersion of energy, we're actually not dispersing as much energy anymore. However, we do have a negative delta G, and we can play around with that to figure out what kinds of temperatures we need for this reaction. So remember, delta G equals delta H minus T delta S, and if delta S is positive and delta H is negative, it depends on the temperature what will determine whether or not Gibbs free energy the delta G is also negative. So we want it to be negative to be spontaneous. So what it turns out is we need a high heat to help to promote our delta. We need to have some heat to promote our delta S, to promote our delta G being negative. But if it's too high, we get what's called retro Diels-Alder. So remember, retro meaning to go backwards. So we can break our molecule apart. Now, in terms of what's going on in our reaction, remember I kind of drew this before where we had groups on our molecule just as A, B, C, D. If our diene and our dienophile, if we have, let's say, X and A are large and they cause some steric interference, what's going to end up is that when the molecule comes close like this, they're sterics, so the only way the molecule would actually react is if it turns itself around. So let's say, like I said, X and A are large, then your molecule would be in the other orientation. However, wherever all the other groups are on your molecule, they're going to stay there. So if we draw our product from this, A is going to be where A is, B is going to be where B is, and Y and X are going to be where they are, and they're not going to move, okay? So that is one thing that happens. The other thing that happens is, let's say you have a reaction that ends up forming a bicyclic compound, which a lot of times they do. We will, because of energy, and we'll talk more about that later, we form what's called the endo product, and we'll get to that point. But that is the favored product unless you have some weird conditions that cause the exo, but endo is generally preferred. We also see conservation of our molecule in terms of where, what kinds of double bonds we have and so on. But I do want to point out that I mentioned in last video that the S-cis is not very stable. So one of the other reasons you need to heat this reaction is because oftentimes the S-cis is really going to start out with S-trans, and we need to add heat to cause this rotation to the S-cis. We can actually have our molecule reacting in the S-trans, and that's because these p orbitals, they need to overlap. And if the p orbital on one side is just too far, the reaction is not going to happen. So the overlap happens with the p orbitals, but they need to be close to each other. So the molecule needs to be in the S-cis for any reaction to happen. And there are some molecules where the S-cis is always going to happen. Let's draw that again. So for instance, in furan, this rings will never rotate to the trans. There's just no way of rotating ring double bonds in a ring into the trans. So cyclopentadiene, furan, pearl, all of those molecules will only ever react that in the S-cis because they'll only ever be in the S-cis. So let's look at another thing, which is the orientation of our groups on our double bond. When we have what's called the cis-trans, meaning that one of our double bonds, the group, is essentially cis because they're going this way, and the other one is trans because it's going this way, we end up with the groups, so we end up with these methyls, essentially going to be opposite to each other. They're going to end up essentially trans to each other. Okay, so that has to do with when you look at them, they're essentially going to be oriented kind of differently from each other, right? So in that case, we'll see that one gets pushed down and one gets pushed up. When they're both trans to each other, so trans and then trans, what we see is that the methyl groups end up being on the same side. And because they're kind of far away from each other, they kind of just both get pushed up together. So just as a quick thing is if you have cis-trans, which you can think of as different, they're different from each other, the groups are going to end up in opposite to each other. When the double bond is the same, they're both the same, trans-trans or cis-cis, you're going to end up with the groups being on the same direction. So they're going to be same. So that's a good trick to kind of remember that.